Welcome to the deep dive. Ever wonder how we can make computers even smarter at tackling really complex problems? Today, we're exploring a fascinating new idea that actually borrows a page from, well, the human playbook to level up artificial intelligence.
Exactly. We're diving deep into a method called Preference-Aligned Individual Reciprocity, or PAIR for short. If you've been following how AI is evolving to find better solutions faster, you'll find this particularly insightful, I think. We're going to see how it uses inspiration from something as familiar as human-made selection to significantly boost the power of evolutionary algorithms.
Okay, evolutionary algorithms, right. So think of them as problem-solving methods inspired by natural selection. Yeah, you've got a bunch of potential solutions, and over time, the better ones get to reproduce and share their good traits, while the less successful ones don't. This involves selection, choosing who moves forward, crossover where they combine, creating new possibilities, and mutation adding a bit of randomness. Keeps things interesting.
That's right. Now, the traditional way these algorithms select which solutions get to combine can be surprisingly basic. Sometimes it's almost random, or maybe based on a very simple score of how good a solution is right then. And that's a crucial bottleneck, really. These simpler selection methods can hold back an EA's ability to explore a wider range of truly innovative solutions. They can easily get stuck on just, good enough answers without ever discovering the truly great ones.
So PR steps in with a clever twist here. The core idea is making that pairing process much smarter. Instead of those more basic methods, PR taps into the power of large language models, those incredibly capable AI systems we hear so much about, to evaluate and select which individuals should reproduce. And get this, the criteria they use are inspired by how humans choose partners.
Yes, and what's particularly interesting are those specific criteria. The LLM looks at three key things. First, genetic diversity, making sure the individuals being paired have different strengths that could lead to exciting new combinations. Second, fitness level. Naturally, solutions that are already performing well are preferred. And third, what they call crossover compatibility, essentially, how likely the genetic information of two individuals is to combine effectively to create viable and potentially even better solutions.
Right. And to see just how well this human-inspired approach works, the researchers put PIR up against a recent technique called LLM-driven EA, or LMEA. They both tackled a classic challenge, the Traveling Salesman Problem, TSP. Finding the absolute shortest route to visit a list of cities and get back home.
Exactly, a tough nut to crack. And the results are quite telling. The research showed that PAIR consistently outperformed LMEA. It found better solutions and reached those solutions more quickly. This was especially true when PAIR was combined with a version of the LLM they called a flash thinking model. It really suggests that bringing this more nuanced, preference-based selection can give evolutionary algorithms a significant edge.
Okay, let's dive a bit deeper into these evolutionary algorithms then. Beyond the basics we just covered, where exactly do these limitations of traditional selection really become a problem?
Well, as we said, EAs work with a population of solutions evolving over generations. Selection, crossover, mutation. The key issue is in that selection phase. If the algorithm focuses too narrowly just on the very best performers each time, it can quickly lose diversity in the population.
Oh, okay.
Think of it like only breeding from the absolute tallest people. You might get taller on average, sure, but you could lose other valuable traits along the way. This lack of diversity in EAs means the algorithm can get trapped in what we call local optima.
Right, solutions that are good, but not the absolute best possible.
Exactly, and the algorithm has become too specialized, too uniform to find anything better. Researchers have known this is a challenge for a long time. It's mentioned in foundational work going way back.
So these powerful algorithms have this built-in risk of getting stuck. Now let's switch gears slightly to large language models. We hear so much about them. How does their ability for in-context learning play a role here?
Yeah, what's truly remarkable about LLMs is their ability to learn new tasks just from examples given in a prompt that's in context learning. Groundbreaking work, like with GPT-3, really showcased this few-shot learning. You give it a few examples, and it gets it. And later research showed how, with carefully crafted prompts, LLMs could even tackle complex reasoning by breaking things down. Chain of thought prompting. This adaptability, this ability to perform based on the context you provide, has opened up really exciting avenues for using LLMs as intelligent guides in optimization problems.
Okay, so LLMs can learn and even reason based on prompts. Before PAIR came along, how were people trying to use these powerful models with evolutionary algorithms? What did that landscape look like?
There were definitely efforts already underway. A significant one was the LLM-driven Evolutionary Algorithm, or LMEA, framework. Here, researchers explored using LLMs not just for selection, but also for other steps like crossover and mutation.
Oh, interesting.
Yeah, the idea is to prompt the LLM to generate new potential solutions based on descriptions of the current ones. One notable feature of LMEA is its adaptive temperature mechanism. Think of it like a dial controlling randomness in the LLM's suggestions, trying to balance exploring new ideas with focusing on promising ones.
Okay.
But while LMEA was a really innovative step, the creators of PAIR noticed it didn't specifically focus on the selection process itself, not in terms of individual preferences and maintaining that crucial diversity.
So that's the specific area pair targets, right? Honing in on making the selection strategy smarter. So walk us through exactly how this preference-aligned individual reciprocity pair works. What are the key steps?
Precisely. The core inspiration, as we said, comes from human mate selection, this idea of mutual interest, compatibility guiding who ends up together. The pair methodology basically unfolds in three main stages. First, initialization. Start with a random set of potential solutions, standard stuff. Then comes the heart of it, pair-driven selection. This is the novelty. And finally, population evolution, where the selected pairs undergo crossover and mutation to create the next generation. And importantly, PAIR also adopts that adaptive temperature mechanism from LMEA for the LLM to help manage the exploration-exploitation balance.
Let's really dig into that pair-driven selection then. This is where the human-like intuition comes in. How does the LLM act as this evaluator, and what's this analogy about comparing it to a dating app?
Right, so in the pair-driven selection stage, the LLM gets a prompt that basically asks it to play matchmaker, like a system suggesting potential partners on a dating app, maybe. It gets info about each potential solution, its genetic code, so the root in the TSP case and its fitness, how short its tour is. The prompt then tells the LLM to select pairs for crossover based on those three key criteria we mentioned: genetic diversity, fitness, and crossover compatibility.
Okay.
Now here's where it gets really interesting. The LLM doesn't just compare two solutions side by side. Instead, it's told to first pick one individual. Then it effectively role-plays as that individual and tries to select the best and most compatible partner from the rest of the population, considering his own preferences guided by those criteria.
Ah, I see. So it's like saying, okay, if I am this particular potential solution, which other solution here would be the best one for me to reproduce with?
Exactly, to create even better possibilities. And a neat framing.
That's a very relatable way to picture it. So it's not just picking the two highest performers, but thinking about how different they are, how well suited they are to combine. And what about the reciprocity bit in pair?
Well, the reciprocity is sort of reflected in this idea of one individual actively choosing another, based on factors that would likely lead to successful offspring. And, like forming a pair, once two individuals are selected by the LLM, they're removed from the pool for that round of selection without replacement.
Makes sense.
But to make sure the LLM still has a good range of options later, the offspring generated in earlier pairings within the same generation are actually added back into the selection pool for later pairing decisions.
Oh, okay. So it keeps the options fresh.
Yeah, it gives the LLM a wider variety of profiles to consider as things progress.
All right. So after this more thoughtful selection, the chosen pairs do the standard crossover and mutation. Then the whole cycle repeats. Now, testing this, they use the Traveling Salesman Problem. Why TSP, and how did they set up the experiments?
TSP is a real workhorse for evaluating optimization algorithms. It's easy to grasp, but gets incredibly complex fast as you add more cities. A good benchmark. They compared PAIR against the LMEA baseline across several TFP versions, different numbers of cities from 10 up to 25, and different layouts, cities scattered randomly or clustered together, called Roux and Clue instances.
Okay.
In their main experiments, they used the Gemini 2.0 Flash Experimental LMM for both PAIR and LMEA. And crucially, to make sure they were really isolating the impact of the selection method, they kept other factors consistent. Same population size, 16, same max generations, 250, and they used that same adaptive temperature mechanism from LMEA in both runs.
Got it. Fair comparison. And what were the crucial findings when they compared PAIR and LMEA using this standard Gemini Flash model? What did that first set of results show?
That first set looked at the optimality gap, basically, how far the algorithm's best solution was from the known perfect solution as a percentage. What's really notable is that PAIR outperformed LMEA in 5 out of the 8 different problem types they tested.
Wow, okay.
For instance, in one called Clue 15, PAIR achieved an average optimality gap that was 38% or even lower than LMEA's. That's a big difference. It strongly suggests PAIR was significantly better at finding solutions much closer to the ideal in several cases.
That is a pretty substantial improvement. Now, you also mentioned using a flash thinking model. What happened when they ran pair with that enhanced LLM?
Ah, yes. The results there were even more impressive. When pair was combined with the Gemini 2.0 flash thinking experimental LLM, its performance jumped significantly. This combination actually outperformed both the original LMEA and pair with the standard flash model across all 8 of the TSP problems.
All 8.
All 8. And the improvement margins were quite remarkable too, reaching up to, I think, 57.7% better in the Clue 20 problem. It really underscores the potential of using these more advanced LLMs, the ones with stronger reasoning capabilities within the pair framework.
It wasn't just about getting a better final answer, right? The way the algorithms progressed, the diversity of solutions, that also gave insights. They looked at convergence patterns and population diversity.
Exactly. They analyzed how the algorithms converged over time. It showed that while LMEA might have reached a solution faster in some simpler 10-city problems,
Okay.
pair generally achieved better final results in the more complex scenarios. And it seemed better at escaping those local optima we talked about. And when pair used the flash thinking model, its convergence was superior across all problem types, just better overall progress.
And the diversity.
Right, they looked at population diversity measured by how much the tour lengths varied within the population at any given time. They found the flash thinking model consistently led to higher variance, more diversity.
Which is good, right?
Exactly. It suggests maintaining a more diverse set of potential solutions help the algorithm explore the problem space more effectively, avoid getting stuck, and ultimately converge to better outcomes. The researchers basically concluded that these more reasoning-focused LLMs seem better at the pair selection process, both locally keeping the population diverse and globally finding better final solutions.
So to summarize these key findings, it really seems like pair's intelligent preference-based selection is the engine behind its improved performance. It's not random searching, it's strategic choosing based on diversity, fitness, compatibility.
Precisely. Pair's approach allows for a more effective balance between exploring new possibilities, exploitation, and leveraging good solutions already found, exploitation. The fact that the flash thinking model did so much better really highlights how important the LLM's reasoning abilities are for making these nuanced pairing decisions. And it also reinforces those well-established ideas in evolutionary algorithms about needing diversity to avoid getting stuck too early.
Of course, using these advanced LLMs probably isn't free, computationally speaking.
Well,
What are some limitations here?
That's a very important point, yeah. The computational cost of using LLMs for selection is definitely a significant limitation compared to the very fast, often random selection in traditional EAs or even LMEA's approach. Querying these powerful models for each selection step, especially with larger populations or more generations, can be quite resource-intensive, time and money.
Right.
Also, while the TSP results are very encouraging, more research is needed to see how well pair generalizes. Does it work as well on completely different types of optimization problems? We don't know yet.
And in terms of the research itself, what specific gap in the existing work on combining LLMs and EAs was this study aiming to fill?
They specifically identified that while people were using LLMs for various parts of EAs, there wasn't a strong focus specifically on enhancing the selection mechanism itself through this idea of preference modeling and actively managing diversity. Pair directly tackles that gap by introducing a more intelligent, strategic way to choose who reproduces.
Gotcha. And before we wrap up, the study mentioned why they focused the comparison mainly on LMEA. Could you just briefly explain their reasoning there?
Certainly. They gave a few key reasons. First, they'd noticed LMEA's performance seemed to vary quite a bit depending on which specific LLM you used with it. Second, the original LMEA research had already shown it outperformed another LLM optimization technique and was competitive with traditional TSP solvers, so it was a strong baseline. And finally, pair and LMEA are methodologically quite similar. Both use LLMs to directly perform evolutionary operations, unlike some other methods. So comparing against LMEA allowed for a more direct evaluation of pair's unique contribution, that selection strategy.
Right, makes sense. So to bring it all together then, what are the key takeaways for you, the listener, from our deep dive into pair?
Well, the main findings are pretty clear. Pair, this innovative selection strategy using LLMs to mimic aspects of human mate selection, significantly improves evolutionary algorithm performance. It leads to finding better solutions faster for the traveling salesman problem compared to the LMEA baseline. And furthermore, using more advanced LLMs with enhanced reasoning, like that flash thinking model, really amplifies these benefits, largely by helping maintain a diverse set of potential solutions.
It really gives you that aha moment, doesn't it? Seeing how insights from, well, seemingly unrelated areas like human partner selection can be cleverly applied to make our AI problem solvers much more effective.
Absolutely. And while PAIR shows tremendous promise, the researchers are quick to note, there's still work ahead. Addressing the computational costs is a big one. Testing in a wider range of problems, exploring different ways of prompting the LLMs. They also suggest future work could involve making PAIR more efficient, maybe combining it with other advanced techniques. Lots still to explore.
Definitely. And finally, for you, the listener, as you've journeyed through this deep dive with us, maybe consider this. How might these principles of preference and compatibility, so central to natural selection and now artificial selection with PAIR, apply elsewhere? Could understanding the diversity and fitness of different choices in your own life or work, perhaps, lead to more optimal outcomes in unexpected ways? It's definitely some food for thought. Thanks for joining us on the deep dive.